All right, last class we talked about Lewis structures. All right, we've been building Lewis structures, working on placing those valence electrons around your central atom and connecting it appropriately. All right, so now we're going to take a look at what actual three-dimensional shape does that structure take. And so to think about, or to be able to do that, let's think about point charges. We know that if I have a positive and a negative, opposites do what? Opposites attract. They want to be close together. But if I have two negatives or two electrons, what are they going to do? Like charges do what? Repel. So these two are going to push away from each other. So that means areas that have a bunch of negativity are going to repel. So when we think about when we drew CO2, some of you, remember we said it didn't matter which side that carbon, the oxygen came off of the carbon. So some of you may have drawn it like this. Well, what are bonds made up of? Bonds are made up of electrons. All right? And so those areas are areas of high negativity. So if these two want to get as far away from each other as possible, is this the best illustration of that? No. Where does this other oxygen want to go? It's pushing away. And the way to separate them the most, right? If mom's trying to separate you and your sibling, what does she do? She gets in the middle. All right? And so this oxygen, because of that repulsion, ends up over here if we're looking at its actual shape. And so that's what we're going to look at today is how do these zones of electrons, maybe we even have a lone pair on something. All right? How does that lone pair impact the surrounding electrons and the surrounding domains? So we do that by looking at the VSEPR theory. And what VSEPR stands for is the valence shell electron pair repulsion. And what it tells us is that those electron pairs that result from those valence shells interacting with each other, those pairs are going to repulse other electron pairs. And so that tells us that those electrons want to get as far away from each other as possible. All right, imagine opal magnets that you have. And when you play with them, you know how they like bounce around and move away from each other when you would put the same ends of them together. Same concept here. Imagine moving an area of negativity towards another area of negativity. It's going to move away from it, right? It's going to respond by trying to get as far away as possible. However, they're still all attached to that central atom, so they've got to adjust while staying attached to the center atom. And so the shape that results gets determined by the amount of attachments to the central atom, all right? The central atom is where everything's connected to, so that's what's going to determine the shape that it takes. And so attachments, when we say attachments, let's look at NH3. In NH3, you have 8 electrons to illustrate, and so your Lewis dot ends up looking like this. How many attachments or sides of my central atom are occupied? Well, the central atom's nitrogen. How many things are attached to my central atom? 4. I have 4 attachments because those attachments can either be attachments to other atoms, here's our hydrogens, or attachments to other lone pairs, like you see right here. All right, because this lone pair is negativity. Those are just electrons. Over here, you see that negativity in your bonds and those pairs that are sharing. Over here on the left, we see electron groups on central atoms. So that's referring to attachments. How many things are attached to the center atom? You may also hear it referred to as electron domains. Domains means area, right? If you say it's in that domain, it's in that area. So areas of electrons, that's an electron domain. And so it's talking about wherever there's a bond or a lone pair, all right? Or that's really referred to the number of sides that are occupied. Let's simplify it and just think of it as how many sides of my molecule are occupied? Well, we know from Lewis structures, we can only have 4 sides occupied, so that's why you have a max of 4 electron groups on that central atom. All right, and so the first one, what are 2 attachments to the central atom? Let's take a look at your diatomic molecules. It's H2, F2, Br2, Cl2, I2. right? Your super 7. So H2, I have 2 electrons to place, all right? Here's your bond. There's no true central atom on this. Either one of them that you choose has how many attachments? 1. There's only but one way to attach 2 things together with a straight line other than linear. All right, so that would be the example of 1. For 2, let's look at CO2. So you would draw your Lewis structure, 4 plus 6 plus 6. And here's the structure that you get. And so you're looking at that central atom. How many electron domains or attachments do you have on your central atom? So this is where it helps to think of it as the number of sides occupied. How many sides of it is occupied? 2. There are 4 bonds, but only 2 sides are occupied. All right, so again, you would see that linear shape. That's just getting them as far away from each other as possible. All right, as we move into 3 attachments, let's take a look at BH3. Remember, boron is your oddball. It can be satisfied with 6 electrons. All right, so here's that structure. If we look at the central atom, how many attachments? 3. All right, all of them are in bonds. So I can see all of those attachments there. They're all bonds to different atoms. So then it's a trigonal planar shape. Imagine like a fidget spinner. All right, all on one plane, 3 attachments. And so the shape that your electron groups take is the same shape that you actually see in your molecule. So in what case might you not see one of those attachments? Well, let's take a look at O3. All right, you have oxygen in the middle, oxygen on the side. This is ozone. Now on this one in my central atom, how many attachments? 3 attachments. I've got a single bond, a double bond, and my lone pair. And so my electrons assume a trigonal planar shape. All right, that is the geometry that those electron groups take. But can we see electrons? No, electrons are just energy, right? So one of those attachments is a lone pair. I cannot see it because it's electrons, and I can't see just energy. So it still impacts the surrounding bonds, but we can't see it. So the resulting molecule is bent, all right? So that's why they're no longer going to be linear. You have this lone pair up top pushing them down, but it's an invisible effect, right? Think just like God. We can't see him, but we still feel his impact. Same thing's happening here with your molecules and lone pairs. Take a look going into tetrahedral. CH4. You have 8 electrons to place. Here's what you have. All right, so I have how many electron groups on my central atom? 4. All right, and they're all bonds, so I can see them all, right? I can see all of those electron domains. So my resulting molecule is in the shape of that tetrahedral. Imagine like a little tripod shape. All right? So if I take one of those away, for instance, in NH3, so I have nitrogen in the middle, 8 electrons to place again. So here's 6, 7, 8. How many attachments to my central atom? 4, 3 bonds, 1 lone pair, so a total of 4 attachments. The electron geometry is that tetrahedral, but can I see all of them? No, I can't see what? I can't see that lone pair. And imagine they're invisible, right? Y'all said they look like little ghosts. Good, because they're invisible. And so all you see is that pyramid. So that's why we call it trigonal pyramidal, because it looks like a 3-sided pyramid. All right, tri-pyramid, trigonal pyramidal. So you still have that electron pair at the top repulsing all of your bonds and the electrons in your bonds. You just can't see it. And then lastly, let's take a look at water. All right, so we have H2O, oxygen in the middle, hydrogen. I've got 8 electrons to place. All right, how many electron domains on that central atom? 4, yes, 2 lone pairs and 2 bonds. So again, my electron geometry, the shape of all those electron attachments is a tetrahedral. But can I actually see all of those attachments? No. So this time, tetrahedral electron geometry, that is bent. And so this is what you see. Because these 2 lone pairs, we cannot see them. They're just energy. They're energy that's impacting their surroundings, but we don't see them in that molecule. So throughout science classes, or whenever you've seen something about the water molecule, you usually see it like the Mickey Mouse, right? That's why it looks like this instead of 3 circles side by side, because you have these lone pairs right here that are impacting those bonds and repulsing the electrons in your bonds. What do you notice about the bond angles when there are lone pairs present? What do you notice right here?
No, greater than.
Less than.
Oh.
Yep. Less than. You see your less than signs. Does anybody have any idea why they may have a less than 120-degree angle or a less than 109 when there's a lone pair? All right, so think about in your attachments. Let's take a look at O3. What is different about the lone pair than there is in the atom? What do atoms have in them? At their nucleus, what does an atom have? At the nucleus, what does it have? Protons. Your atoms there have protons in them, right? These hydrogens have protons at their core. And they're surrounded by those electrons. But a lone pair is nothing but negativity. So those protons help balance things out. All right? And this instead is a huge mass of negativity. So it's like you've got a little bit of negativity, because the positivity in the nucleus of the atom balances it out. But when we drop that lone pair there is no positivity to balance it out. There's no nucleus or anything. So that lone pair kind of comes in as the big bully and gives these an extra little push because of that big mass of negativity. It's got a little extra repulsion to those bonds that surround it. And so that's why you see that less than 120. All right, make sense? So let's take a look at that for those of you who are really visual people. Let's take a look at this. So you see if you add a single bond, what shape is it?
Linear.
Linear. It's a straight line. If I add another one, the best way for them to get far apart is what?
Linear.
Linear. When I add another one, what do you notice happens?
Triangle.
What do those 2 that are there do?
They move away closer.
They move away. They get a little bit closer to each other so that they can move away and adjust for the additional bond that's coming in. Why do they do that?
Because of the energy, like, repelling it.
Yes, because of that repulsion. And so right now, they're all pushing against each other, holding them in those bond angles. And so there's where you see your trigonal planar. Bring in another bond. Here's your 4. And look, it's no longer in one plane. Imagine like 2 V's. You put their points together and then turn, right? And so, or here's your tripod. All right, and so you've got a 3-dimensional shape now. When those are replaced with lone pairs is when you start to see different shapes. So look, here I have my trigonal planar. If I replace that with a lone pair, the only thing I can actually see is what? bent. All right, so here you have trigonal planar, they're both the same. But when we replace one, all we actually see is bent because your lone pair can't be seen. Then let's see, you have your tetrahedral. Here's what you have if all of them are bonds. But if I replace one of those bonds with a lone pair, because imagine that tripod and you take the top off. Right? So here's what you have. Take that away. All you see is that resulting pyramid because the top is now invisible.